Hello, and thank you for attending our presentation today. My name is Brian Adamson, and I am the Business Development Manager for John Crane Filtration. Our presentation is called The Role of John Crane Filtration in the Energy Transition Market. Today we will be discussing the following subjects. We'll be discussing where filtration fits into the energy transition areas, such as hydrogen, methane reduction, and carbon capture. We'll discuss the filtration products that fit into these areas and then summarize with some key takeaways. Let's look at hydrogen production applications first. This slide is pretty busy, so we won't go into the system details. We'll look at where the filtration applications are. So we have a typical here we have a typical electrolyzer system. In this case, is a 50 megawatt electrolyzer. Electricity is supplied by solar and wind power. As the water is supplied by the pump here, it goes through into a resin filter. The resin filter can be overcome by a high volume dirt and could fill up fast. The water needs to be filtered with a coarse filter to increase the life of the resin filter. Here we're showing a John Crane automatic backflush filter. The water is then goes to a deionized water tank and then pumped into the electrolyzer. From there, we have hydrogen coming out here and oxygen coming out here. At this point, both gases can be filtered for both solids and liquids using high flow coalescers, both sides. See those here. Any water that is removed can go back into the system to be recycled. Water that is separated from these high flow coalescers. Both gases are compressed and then sent out into the market. The centrifugal compressors here will have lube oil filters and also seal gas filters. So the hydrogen life cycle goes from hydrogen production to transportation, and finally to end use. Filters are used throughout the cycle, including the end use. The end use is a series of processes before it goes into the vehicle. At first, the hydrogen arrives as liquid, either by tanker truck or pipeline. It must first be converted into a gas before it can be used. Here it passes through vaporizer towers that heat the liquid until it turns into a gas. Before hydrogen goes into the vehicle, it must be compressed to high pressure, up to 10,000 psi or 700 bar. There are two standards for hydrogen compression: half pressure of 350 bar or full pressure 700 bar. Higher pressure translates into higher range. On a modern fuel cell vehicle such as the Toyota Mirai, for example, a full fill at 700 bar equals 312 miles of range, which is on par with the gasoline-powered vehicles. Hydrogen sits in storage tanks, just like gasoline, only above ground. To prevent expansion and to maintain energy density while being pumped at high pressures, hydrogen must be cooled through a heat exchanger before it passes through the pump. Cooling prevents the vehicle's onboarding tanks from overheating. Finally, the hydrogen goes to the pump to fill your vehicle. At this point, the hydrogen is filtered. It is essential that the hydrogen be very clean when it is in storage on the vehicle. The process that the vehicle goes through to convert hydrogen to power cannot handle any contamination. One active project that we have is a major US-based operator of hydrogen liquefaction. The process uses cryogenic turbo expander compressors that uses John Crane filtration for both lube oil and seal gas. Now we move to the subject of methane reduction. I know what you're thinking. How can a filter reduce methane emissions? Well, besides the leakage from the usual O-rings or gaskets and valve stems, we will be discussing how the seal gas filters protect the shaft seals on large centrifugal gas compressors and keeps them running efficiently. Because solid particles and liquid particles tend to wear out seals and cause increased fugitive emissions. Well, the negative impacts to methane emissions. The environmental impact is substantial. Methane emissions represent 18% of the total climate impact. Natural gas loss annually valued at 27 billion. Unfortunately, this tarnishes the reputation of natural gas as clean bridge fuel for power generation or large fleet vehicles such as garbage truck or fork trucks. This is a global problem requiring a global solution. This chart shows that North America region is one of the leading methane emitting areas of the world. Most of the leading areas of the world are using old technology for sealing compressors. This old technology is seal oil technology. Centrifugal compressors with oil seals are a leading methane emission source. Natural gas systems make up a big chunk of methane emission sources, but as you can see, enteric fermentation or cow burps is still the biggest source. We will stick to the technology we are familiar with. Centrifugal compressors fall under the category of natural gas systems and are around 6% of the natural gas systems that are emitting methane. That's a big amount for one type of machinery. In the US, this equates to 24 billion cubic feet or $72 million worth of natural gas annually. Centrifugal compressors used in the oil and gas industry are for applications such as gas injection compressors, pipeline compressors, natural gas processing, natural gas transmission and storage. Centrifugal compressors use a spinning turbine to pressurize gas. The rapidly rotating main shaft of the compressor is generally sealed with one of two technologies. Either the use of pressurized oil in a seal oil system, or the use of pressurized gas from either the gas that the compressor is compressing or a second source, such as pressurized nitrogen. Compressors in our discussion today are compressing natural gas and are also using it for the seal gas. Traditional technology uses wet seals to circulate oil to seal the narrow gap between the shaft and the housing. This seal oil absorbs significant amounts of the natural gas that must be removed from the oil before recirculation. Typically, the gas removed from the seal oil is directly vented to atmosphere, resulting in substantial emissions. In this case, for most of the worldwide emissions from compressors, the United States still has quite a few seal oil systems as well, but are being converted to the new technology, which is dry gas seals. Dry gas seals avoid the use of seal oil. Any emission from dry gas seals can be sent directly to flare or back into the process, substantially reducing costs and substantially reducing emissions. These types of seals require very good filtration as well as coalescing of any liquids that can be found in the gas. The filter must remove solids and liquids from the gas stream before it enters the seal. Filtration leads to an excellent opportunity in supporting dry gas seal retrofits to reduce methane emissions. Next, we'll discuss CCUS, or in other words, carbon capture, utilization, and storage. Along the carbon capture value chain, we have many opportunities to supply filtration. Pumps and compressors are used at every level of the value chain, and they need filtration to perform efficiently. Specifically, however, there are many opportunities for filtration during the carbon capture process. For instance, in this absorption type process, the feed gas needs a filter to remove solid contaminants as well as liquids. The makeup solvent used to absorb CO2 needs to be filtered as it is added to the process. And finally, the CO2 is compressed using a centrifugal compressor, therefore needing seal gas filters and lube oil filters. Even in an adsorber type system for separating CO2, filtration is needed. This system reduces the number of components that the absorption process uses. But the adsorption column, however, is very sensitive to contamination in liquids, therefore needing a high flow coalescer. Also, the compressor at the end of the process needs seal gas filters and lube oil filters. An application that we have experience with is one of the largest LNG projects that has CO2 removal and storage. There are 3 centrifugal compressors with John Crane Type 28 dry gas seals. These compressors will inject CO2 2 kilometers below ground. We are also providing seal gas filters and lube oil filters to support the compressors. Okay, what John Crane products will be used in this energy transition market? John Crane has all kinds of products and applications applicable for mostly centrifugal compressors and as well as gas turbine applications for the power industry. Also, we have products for reciprocating compressors, air compressors, and pumps. We have 2 types of filters, liquid filters and gas filters. Liquid filters, we have transfer valve products, lube oil filters, fuel oil filters. And for gas, we have seal gas filters and fuel gas filters, and all can be made into small little package systems. Lube oil filters will be used to filter the lube oil to engineered bearings on centrifugal compressors. We manufacture our lube oil filters in a unique way. We use forgings instead of welded vessels. The forgings can give us many advantages. It can be a very small, compact system. There are no welds, so there's no welding requirements or testing. There's no deformation during manufacture. We have a perfect seal using O-rings in the cover. This design code can meet manufacturing design codes from all around the world, including AS1210 for Australia, CRN for Canada. Our standard lube oil filter series starts off with a small little 1-inch filter all the way up to an 8-inch filter, all using machined bolted connections and no welds. We also have a small cast steel lube oil or liquid filter for any type of John Crane mechanical seal application for seal flush. Small little, up to 10 gallons per minute. Next, we'll talk about the seal gas filters, specifically the FCF model. Redefining seal gas filtration for the API 692 standard. Early on, when dry gas seals were first introduced, the late 1980s, filtration for these systems consisted of 2 single laboratory grade filters because they were the only coalescing filters available at the time. Unfortunately, the housings of these special filters didn't meet the stringent duty that is required for the API industry. What was needed was a filter that could do the delicate coalescing work, plus have a rugged filter housing required for API applications. The housing needed to be an ASME designed vessel. It needed to have bolted covers, not screwed on bowls. It needed to meet pressure vessel standards from all over the world. It also needed to be duplexed together so the filter element can be changed without shutting the system down. Hand valves can create a shutoff of the gas if done incorrectly. Machined forged housing was the only answer. Indifil, a new company to the market, introduced this design early on in the early 90s. It is a hybrid, you could say, which included the rugged housing, but also had the capability to do the delicate coalescing that these systems needed. It has zero leak transfer valve for duplexing the two filter housings, thus eliminated the hand valves. This design quickly became the industry standard for a good many years. Many filter companies followed suit. This is the look of seal gas filters today. John Crane bought Indifil in 2008. John Crane has been in the filtration business ever since. We also added innovations such as compact double block and bleed transfer valves. We could add accessories such as sight glass level indicators, level switches, level and differential pressure transmitters, and other liquid monitoring equipment. This bolted machine design quickly led to many new innovations, including this two-stage filter assembly that has a built-in knockout section in the first stage, along with the coalescing section in the second stage, and a single drainer vessel with its own transfer valve. So it will drain the filter housing that is in service. Within that vessel is an automatic drain device that will drain the vessel when the liquid level reaches a predetermined level. There are two specifications that outline requirements for sealed gas systems and filtration. One is the API 614, which is the long-used specification since the 1990s. And then the newly released API 692. API 614 is a lube oil specification that included the sealed gas systems because there wasn't a specification for sealed gas systems in the oil and gas industry at the time. It required duplex filter with a continuous flow transfer valve, 4 micron absolute particulate filtration, 4 micron absolute mist filtration. Filter had to be sized using 3 times the flow with a pressure drop of 10 kPa across the element only. API 692, which came out recently, is specifically for sealed gas systems only. It became a stricter specification for systems and filters. It required 1 micron absolute particulate filtration, 1 micron absolute liquid mist filtration. Filters would be sized for 3 times the normal flow and be less than 10 kPa across the entire filter assembly, not just the filter element, as before. This caused the filters to increase in size substantially. All the innovation that Indifil had was great, but now with the new API 692, we needed to do something to meet the tough sizing requirements. We needed to go to our product development team to redesign the filter to reduce pressure drop. This new design will lead to lower cost sealed gas filters and in turn lower the cost of sealed gas systems. The result of that development is the new John Crane FCF series sealed gas filter. FCF stands for flow conditioned filter. It is the first of its kind to be designed using CFD software to reduce the pressure drop to its absolute minimum. During this development, we discovered many innovations that put this filter at the forefront of technology. Using CFD software, we discovered the gas at the point where it goes into the filter element is very turbulent and it created a vortex. This vortex was causing a high velocity area in the element where the flow is concentrating the most. Unfortunately, this area is where most of the liquid is draining on the outside of the filter element. This high velocity could cause some liquid carryover. John Crane developed a unique laminar flow technology to remove the vortex from the gas flow. Additive manufacturing is used to create a flow straightener at the inlet of the filter element. This honeycomb design could only be created efficiently, that is, using 3D printing. It became one of the first John Crane products to be produced by 3D printing for commercial use. The result is the efficient use of the full filter element media and reduced the risk of droplet re-entrainment, decrease in operational pressure drop to 50%. For more information on all the innovation we discovered, please send your comments or questions in the chat box. We can tell you that these innovations led to the best seal gas coalescing performance in the industry. Next, we'll talk about the high flow coalescer HFC model. HFC, liquid gas coalescing filter technology, very high separation efficiency of 99.9%. Extended the life of filter elements over 12 months to reduce operation cost. Increased gas handling capacity, 210 actual cubic meters per hour per element. And the welded pressure vessel design reduces investment costs. We also use what's called our length time to diameter ratio for the element to have optimal flow through the element, reducing any of these high velocity hotspots. Next, talk about the multi-purpose filter, MPF filter. The MPF is an automatic backflush filter with an integral cyclone separator in the bottom, first stage. Either a scraper type or a backflush unit for final filtration. The filter will go through the backflush sequence after a predetermined time or pressure drop. There's a max pressure of 232 psi, max flow of 210 gallons per minute, and 25 micron filtration. Reliable removal of suspended solids up to small, fine particles, reduced operational costs and extended maintenance intervals, more efficient water treatment for reduced freshwater consumption. And next, the inline hydrogen filter. As described before, the hydrogen end usage requires a special filter. We introduce our high pressure inline filter. It is capable of 1,000 bar or 14,500 psi. It can be installed on the hydrogen pump at the filling station and will filter the hydrogen before it goes into the vehicle. As you can see, John Crane has a strong portfolio of filtration products to fit your needs in the energy transition market. We have many ongoing projects right now and are poised to take on many more in the future. The landscape is changing and we are ready for that change right now. Thank you very much for listening.